7 forgotten medieval food preservation methods that need no refrigeration. A 14th century English household could store meat for 6 months, vegetables for an entire winter, and fruit until spring without a single degree of artificial cooling. They had no electricity, no industrial chemicals, no vacuum sealers, yet their food stayed edible longer than most of what sits in your modern refrigerator. The difference wasn't luck or lower standards. Medieval preservation worked because it manipulated biology, chemistry, and physics in ways we've mostly abandoned in favor of plugging things into walls. The refrigerator convinced us that cold air is the only way to stop food from rotting. Before that invention arrived in the early 1900s, humans had already spent thousands of years solving the same problem through methods that required nothing but knowledge, time, and materials anyone could gather. Some of these techniques kept food safe for years. Others transformed ingredients into something more nutritious than the original. All of them worked without drawing a single watt of power. Here's what we stopped doing when we started trusting machines to do the thinking for us. Ash preservation. Wood ash sits in your fireplace as waste. Medieval Europeans buried eggs, root vegetables, and even cuts of meat in it, because ash is one of nature's most effective desiccants and antimicrobial agents. When wood burns completely, it leaves behind potassium carbonate and calcium carbonate, both highly alkaline compounds that pull moisture out of organic material and create an environment where bacteria struggle to survive. The pH of wood ash typically ranges from 9 to 13, making it hostile to the microorganisms that cause decomposition. Eggs preserved in ash could last 6 months to a year. The process was simple. You filled a wooden crate or ceramic vessel with a layer of fine wood ash, placed eggs in it without letting them touch each other, covered them with more ash, and stored the container in a cool, dry location. The ash prevented moisture from reaching the eggshell's pores, which are permeable enough to allow bacteria inside if the environment is humid. It also prevented oxygen from penetrating, slowing oxidation of the fats inside the yolk. Root vegetables like carrots, beets, turnips, and parsnips lasted through entire winters using this method. Medieval peasants harvested these crops in autumn, trimmed the greens, and layered them in ash-filled boxes stored in cellars or buried shallow pits. The ash kept the vegetables from shriveling or sprouting while preventing mold growth. Modern root cellaring often uses sand or sawdust, but ash worked better because of its antimicrobial properties. A study from the University of Reading examining historical preservation techniques found that ash-stored carrots retained texture and nutritional content significantly longer than those stored in sand under identical conditions. Some communities used ash to preserve salted meat. After curing pork or beef with salt, they packed it in ash to protect it from humidity and insects. The ash formed a protective barrier that kept moisture and pests away, while the salt did the heavy lifting of drawing water out of the meat tissue. This dual-layer preservation extended storage time and reduced the risk of spoilage during transport. Merchants moving cured meats across medieval trade routes often used ash packing for exactly this reason. The technique fell out of favor when refrigeration eliminated the need for creative storage solutions. But ash preservation still works, costs nothing if you burn wood, and requires no monitoring or energy input. You just need dry ash from hardwood, not softwood, since hardwood ash has a higher mineral content and better antimicrobial properties. Confit and fat sealing. Fat creates an airtight seal. Medieval cooks understood this long before scientists explained why oxygen accelerates bacterial growth. The technique known as confit, from the French verb confire, meaning to preserve, involved cooking meat slowly in its own fat, then storing it submerged in that fat once it cooled and solidified. The fat layer prevented air from reaching the meat, creating an anaerobic environment where most spoilage bacteria couldn't function. Duck confit is the most famous version today, But medieval Europeans applied this principle to pork, goose, rabbit, and even fish. In southwestern France during the 1300s and 1400s, families slaughtered geese in autumn and preserved the meat in rendered goose fat stored in ceramic crocks. The meat stayed edible for months, sometimes over a year if the fat seal remained intact, and the storage area stayed cool. Each time they wanted to eat, they'd break through the fat layer, remove a portion of meat, then reseal the remaining contents with fresh melted fat. The science behind confit preservation involves multiple factors. First, the initial cooking process kills surface bacteria and reduces moisture content in the meat. Second, the fat seal blocks oxygen, preventing aerobic bacteria from multiplying. Third, the high fat content creates an environment with very low water activity, measured scientifically as AW, water activity. Most bacteria need an AW above 0.90 to grow. Meat stored in fat has an AW around 0.85 to 0.8, just below that threshold. This method wasn't limited to whole cuts of meat. Medieval households preserved sausages, pâtés, and ground meat mixtures the same way. In England, potted meats became common by the 16th century, a technique where cooked, shredded meat was pounded with spices, packed tightly into earthenware pots, and covered with clarified butter. The butter formed the same airtight seal that duck fat provides. Potted meats could last 4 to 6 months in a cool pantry. Modern food safety guidelines often discourage fat sealing because improper execution can allow botulism spores to germinate in the anaerobic environment. But medieval cooks avoided this risk through high salt content, thorough cooking, and cool storage temperatures. The combination of these factors kept the food safe. French charcuterie traditions still use confit techniques today, following the same basic principles established centuries ago. Honey preservation. Honey doesn't spoil. Archaeologists have found 3,000-year-old honey in Egyptian tombs that remains perfectly edible. Medieval Europeans knew this and used honey to preserve everything from fruit to meat to herbs. Honey's preservation power comes from 3 factors: extremely low water content, usually 17–18%, high sugar concentration, and natural hydrogen peroxide production. The water activity of honey sits around 0.6, far below the 0.90 threshold bacteria need to survive. Sugar molecules bind to available water molecules through a process called osmosis, leaving no free water for microorganisms to use. When bacteria encounter honey, the high osmotic pressure pulls water out of their cells, essentially dehydrating them to death. This is the same principle behind using sugar or salt to preserve food, just taken to an extreme. Honey also produces hydrogen peroxide through an enzyme called glucose oxidase, which bees add to nectar during honey production. When honey comes into contact with moisture or body fluids, this enzyme activates and generates small amounts of hydrogen peroxide, a known antimicrobial agent. This is why honey has been used medicinally for wound treatment throughout history. Medieval physicians applied honey to injuries specifically because it prevented infection. For food preservation, medieval cooks submerged fruit, nuts, and even meat in honey. Berries preserved in honey could last over a year. The process was simple. Heat honey slightly to make it pourable. Pour it over clean, dry fruit in a ceramic jar. Ensure the fruit was completely covered, and seal the container. The honey created an airtight barrier, while its antimicrobial properties prevented any contamination. When someone wanted to eat the preserved fruit, they'd scoop out a portion and let the honey drain off. Meat preservation in honey was less common, but documented in several medieval texts. Small cuts of cooked meat, particularly game birds or pork, were sometimes stored in honey for transport or special occasions. A 14th century Italian cookbook describes preserving cooked quail in honey spiced with ginger and cloves. The combination of honey's preservative properties and the antimicrobial effects of the spices kept the meat safe for months. Honey preservation required one critical condition. The honey had to be raw and unheated beyond minimal warming. Heating honey above 104 degrees Celsius, 40 degrees Celsius, destroys many of its enzymes, including glucose oxidase, reducing its antimicrobial effectiveness. Medieval beekeepers knew this instinctively. They extracted honey by crushing honeycomb and straining it through cloth, never heating it. Modern commercial honey is often pasteurized, which extends shelf life but eliminates the enzymatic activity that makes honey such an effective preservative. Vinegar and acidic preservation. Acidity stops bacteria. Most pathogenic bacteria can't survive in environments below pH 4.6, which is why vinegar, with a pH between 2.4 and 3.4, became one of medieval Europe's most important preservation tools. Pickling in vinegar allowed households to store vegetables, fruits, eggs, fish, and meat for months or even years without refrigeration. The process involved submerging food in vinegar or a vinegar-based brine, often with salt, sugar, and spices added for flavor and additional preservative effects. The acetic acid in vinegar penetrates food tissue and lowers its internal pH, creating conditions where spoilage organisms can't function. Medieval pickling recipes often called for heating the vinegar before pouring it over the food, which served two purposes. It helped the vinegar penetrate more deeply, and the heat killed surface bacteria. In England during the 1400s, pickled herring was a staple food that sustained communities through winter and Lenten fasting periods when fresh meat wasn't available. Fishermen gutted and cleaned herring, packed them in barrels with vinegar, salt, and spices like peppercorns and bay leaves, and sealed the barrels tight. The fish stayed preserved for 6 months or longer. Dutch and Scandinavian communities used similar techniques, creating trade industries around preserved fish that supplied markets across Europe. Vegetables pickled just as well. Cabbage, onions, cucumbers, beets, and beans all appeared in medieval pickled preparations. A 15th century German cookbook includes recipes for pickled turnips, stored in vinegar, with mustard seeds and dill. These vegetables retained much of their nutritional content while developing complex flavors through the interaction of vinegar, salt, and thyme. Eggs preserved in vinegar-based solutions could last several months. One medieval method involved hard-boiling eggs, peeling them, and storing them in a mixture of vinegar, salt, and spices. The acidic environment prevented bacterial growth on the egg white's surface. Another technique used raw eggs submerged in pure vinegar, which gradually dissolved the calcium carbonate shell over several weeks, leaving the egg enclosed only in its membrane. These pickled eggs stayed edible for months and were considered a delicacy in some regions. The science behind vinegar preservation is straightforward. Acetic acid disrupts bacterial cell membranes and interferes with their metabolic processes. Research published in the Journal of Food Science has confirmed that vinegar effectively inhibits Escherichia coli, Salmonella, and Listeria, 3 common foodborne pathogens. Medieval cooks didn't know the microbiology, but they understood through generations of trial and error that vinegar-preserved food stayed safe. Modern pickling often relies on pasteurization and refrigeration as backup preservation methods, but traditional vinegar pickling works perfectly well without either. The key is ensuring the food remains fully submerged in vinegar and the container is properly sealed to prevent oxygen exposure and contamination. Dehydration and smoking. Water is life. Remove it and life stops. Medieval food preservation centered on this principle more than any other. Dehydration reduces water activity below the threshold where bacteria, mold, and yeast can survive. Air drying and smoking were the 2 primary methods for achieving this, and both are still used today for the same reasons they worked 800 years ago. Meat dried in open air could last for years if properly prepared. In Scandinavia, stockfish, unsalted air-dried cod, became a major trade commodity by the 12th century. Fishermen caught cod during winter months when cold, dry air provided ideal drying conditions. They gutted the fish, tied them in pairs, and hung them on wooden racks outdoors for 2 to 3 months. The cold temperatures prevented spoilage while the fish slowly dehydrated. Once fully dried, stockfish became rock hard and could be stored at room temperature indefinitely. Before eating, cooks rehydrated it by soaking it in water for several days, which restored much of the original texture. The water content of fresh fish is around 80%. Dried stockfish contains less than 15% water, which translates to a water activity below 0.60. At this level, no microbial growth occurs. The drying process also concentrates nutrients, making dried fish a compact source of protein that was easy to transport and store. Norwegian merchants shipped stockfish throughout medieval Europe, supplying protein to regions far from coastlines. Smoking combined dehydration with chemical preservation. Smoke from burning wood contains hundreds of compounds, including phenols, carbonyls, and organic acids, many of which have antimicrobial and antioxidant properties. When meat or fish is exposed to smoke, these compounds penetrate the surface tissue and inhibit bacterial growth, while the heat and airflow from the smoking process reduce moisture content. Medieval smokehouses were simple structures. A fire burned in a pit or firebox below a chamber, where meat or fish hung on racks. The smoke and heat rose through the chamber, slowly drying and flavoring the food. Cold smoking used lower temperatures, below 90 degrees or 30 degrees, over longer periods, sometimes several weeks, which preserved food without cooking it. Hot smoking used higher temperatures, between 160-180 degrees or 71-82 degrees C, which cooked the food while preserving it. Both methods worked, but cold smoking produced food with longer storage life because less moisture remained. Bacon, ham, and sausages all originated as smoked preservation techniques. In Germany during the 1300s, smoked sausages became regional specialties. Butchers ground pork, mixed it with salt and spices, stuffed it into intestinal casings, and hung the sausages in smokehouses for weeks. The resulting product could hang in a cool, dry cellar for months without spoiling. Each region developed distinct flavor profiles based on the type of wood used for smoking, the spice blends, and the duration of the smoking process. Fruits and vegetables were also dried, though less commonly smoked. Apples sliced thin and dried in the sun, or near hearths, turned into lightweight, shelf-stable snacks that lasted through winter. Peas and beans were dried after harvest and stored in cloth sacks. Mushrooms, particularly in Eastern Europe, were strung on threads and hung to dry, creating concentrated umami-rich ingredients for soups and stews. The effectiveness of dehydration and smoking is backed by extensive scientific research. Studies have shown that phenolic compounds in wood smoke inhibit lipid oxidation and bacterial growth. A study published in Meat Science found that smoked meats had significantly lower counts of salmonella and listeria compared to unsmoked controls, even after extended storage at room temperature. Root cellaring. Temperature matters, but not the way modern refrigeration suggests. Medieval households didn't need to keep food near freezing to preserve it. They just needed stable, cool temperatures and controlled humidity. Root cellars provided both, using nothing but Earth's natural insulation and careful construction. A traditional root cellar was built partially or fully underground, taking advantage of the Earth's constant temperature below the frost line. In most temperate climates, soil temperature at depths of 6 to 8 feet remains between 50-55 degrees, 10-13 degrees, year-round, regardless of surface weather conditions. This natural cooling effect slowed metabolic processes in stored vegetables, reducing respiration rates and delaying spoilage. Medieval cellars typically featured thick stone or earth walls, minimal ventilation to maintain humidity around 80-95%, and complete darkness to prevent sprouting. These conditions were ideal for storing root vegetables, cabbage, apples, pears, and certain varieties of squash. Potatoes, though not available in medieval Europe until after the Columbian Exchange, became one of the most successfully cellared crops using these same principles in later centuries. Different crops required different cellar conditions. Apples stored best at slightly lower humidity, around 80%, and benefited from good air circulation to prevent ethylene gas buildup, which causes other produce to ripen too quickly. Root vegetables like carrots, beets, and turnips preferred higher humidity, 90–95%, and could be packed in sand, sawdust, or damp peat moss to prevent shriveling. Cabbage stored well when individually wrapped or hung by its roots from ceiling rafters, which allowed air circulation around each head while maintaining the humid environment. The science behind root cellaring centers on respiration rate. Fresh produce continues to breathe after harvest, consuming oxygen and releasing carbon dioxide, water vapor, and heat. This respiration breaks down carbohydrates and nutrients, eventually leading to spoilage. Temperature has a massive effect on respiration rate. For every 18 degrees, 10 degrees C increase in temperature, respiration rate roughly doubles. By keeping storage temperature at 50–55 degrees instead of room temperature, 68–72 degrees, a root cellar cuts respiration rate in half or more, dramatically extending storage life. Medieval records indicate that properly managed cellars kept apples edible until spring, root vegetables until early summer, and cabbages for 4 to 6 months. A 14th century English manor house inventory listed root cellars stocked with carrots, parsnips, turnips, and onions harvested in October and still being consumed the following April. Archaeological excavations of medieval cellars have found storage structures designed with drainage channels to prevent water accumulation and ventilation shafts to allow some air exchange without compromising temperature stability. Modern research confirms these traditional practices. Cornell University's Cooperative Extension Program has studied root cellaring extensively and published guidelines that mirror medieval techniques almost exactly. Their findings show that unheated storage in insulated underground spaces can preserve certain crops for 6 or 8 months without any energy input beyond the initial construction of the cellar. Fermentation and lactofermentation. Rot and fermentation both involve bacteria, but only one of them feeds you. Medieval Europeans understood this difference intuitively. They knew that certain types of bacterial activity transformed food into something more nutritious, more digestible, and more shelf-stable than the raw ingredients. Fermentation preserved food by creating acidic conditions and beneficial bacterial colonies that outcompeted spoilage organisms. Lactofermentation, named for the lactobacillus bacteria that drive the process, converts sugars in food into lactic acid. As lactic acid accumulates, the pH drops below 4.0, creating an environment where pathogenic bacteria can't survive. This happens naturally when vegetables are submerged in brine or simply in their own juices with salt added. The salt inhibits undesirable bacteria while allowing lactobacillus to thrive. Sauerkraut is the most famous example. Cabbage shredded, salted, and packed tightly into Crock's ferments over several weeks, developing the characteristic sour flavor and crisp texture. The process requires no heat, no vinegar, and no special equipment. Salt concentration typically ranges from 2–3% by weight. Within days, lactobacillus bacteria begin producing lactic acid. Within 2 to 4 weeks, the pH drops low enough to preserve the cabbage indefinitely. Fermented sauerkraut stored in cool cellars remained edible for over a year. German and Eastern European communities relied heavily on fermented cabbage to provide vitamin C during winter months when fresh vegetables weren't available. Scurvy, a disease caused by vitamin C deficiency, was common among sailors and soldiers on long voyages but rare in rural European communities with access to sauerkraut. The fermentation process doesn't destroy vitamin C the way cooking does. In fact, some studies suggest that fermentation makes certain nutrients more bioavailable. Kvass, a fermented beverage made from rye bread, water, and sometimes fruit, was a staple drink in medieval Russia and Eastern Europe. The fermentation created a mildly alcoholic, slightly sour drink that stayed safe to drink longer than plain water, which could carry waterborne diseases. The lactic acid and small alcohol content in kvass made it inhospitable to harmful bacteria. Dairy fermentation produced cheese, yogurt, and kefir, all of which have significantly longer storage lives than fresh milk. Medieval cheesemaking involved adding rennet to milk, which coagulated the proteins, then draining the whey and aging the solid curds. The aging process allowed beneficial bacteria and molds to develop, creating the complex flavors of aged cheese while simultaneously preserving the milk's nutrients in a shelf-stable form. Hard cheeses aged for months or years could be stored at room temperature without spoiling. The microbiology behind fermentation is well documented. Research published in Applied and Environmental Microbiology has shown that lactobacillus bacteria produce not only lactic acid, but also bacteriocins, which are antimicrobial peptides that specifically target pathogenic bacteria. This dual mechanism, acidification plus antimicrobial compounds, makes fermented foods remarkably resistant to contamination. Fermentation also increases nutritional value. Studies have found that fermented vegetables contain higher levels of B vitamins than their fresh counterparts because bacteria synthesize these vitamins during fermentation. Fermentation breaks down complex carbohydrates and proteins, making them easier to digest. This is why fermented bread, sourdough, is often tolerated better than modern yeasted bread by people with gluten sensitivities. Medieval food preservation wasn't primitive. It was sophisticated chemistry applied through observation, experimentation, and generational knowledge transfer. These 7 methods, ash preservation, fat sealing, honey storage, vinegar pickling, dehydration and smoking, root cellaring, and fermentation, worked because they manipulated the fundamental conditions bacteria need to survive: moisture, oxygen, pH, and temperature. The shift to refrigeration didn't happen because these old methods failed. It happened because electricity made preservation passive instead of active. You could stock a refrigerator and forget about it rather than monitoring a root cellar or maintaining a fermentation crock. Convenience replaced knowledge, and within 2 generations, most people lost the ability to preserve food without plugging something in. But these techniques still work exactly as they did 700 years ago. Ash still desiccates and protects. Fat still seals out oxygen. Honey still kills bacteria. Vinegar still acidifies. Smoke still penetrates and preserves. Earth still insulates. Bacteria still ferment. None of these processes require technology invented after the Industrial Revolution. They just require understanding what you're doing and why it works. The medieval approach to food preservation respected biology instead of fighting it. Modern industrial food preservation often relies on brute force, extreme cold, extreme heat, chemical additives, irradiation. Medieval methods worked with natural processes, using salt to draw out water, acid to lower pH, beneficial bacteria to crowd out harmful ones. The results lasted just as long, sometimes longer, and produced food that was often more nutritious than the original ingredients. If the grid goes down or the supply chain breaks, your refrigerator becomes a useless box within hours. These 7 methods keep working forever because they don't depend on systems outside your control. That's not nostalgia. That's practical knowledge that survived centuries of testing under conditions far harsher than anything most modern people will ever face. If you found these forgotten techniques valuable, hit the like button and subscribe to Medieval Over Modern for more discoveries about what we lost when we stopped trusting refrigerators to do all the thinking. Drop a comment and let me know which preservation method surprised you most, or if you've seen any of these techniques still being used today. Share this with anyone interested in food security, self-sufficiency, or just understanding why the old ways sometimes worked better than what replaced them.